This is a Thorium Energy Alliance Technology Talk from the inaugural Future of Energy Conference, October 2009. To find out more about thorium energy, please visit thoriumenergyalliance.com. This talk is from Dr. Joe Bonometti, whose topic is What Fusion Wanted to Be, a systems engineering perspective of a thorium energy economy. Many of you have seen Joe's Google Tech Talk, which is fabulous and a miracle that Google supports this sort of technology. And so let's give a hand to Joe. Thank you so much for coming, Joe.
All right, thank you. I'm going to cover a little bit of what my Google Tech Talk, a couple of key points there, and hopefully a few pieces of new information, as well as kind of get everybody excited about maybe moving on. There's two things that we got to do here, I think, and one, we're doing it, and that is education. They say something like, if you need to tell a lie, you tell it over and over until somebody believes it. Well, I always thought the correlate, you tell the truth once and, it's believed. It's apparently not the case. It's going to take a lot of effort. I think we're starting that. I think that's really important. We need to continue. Now, we also need to continue not only on the political front to get funding. If you don't have funding, this program's not going to go much further. But at the same token, we also need to think on terms of what the program might look like, okay? And again, that tailors on who is the ultimate customer. Are you going to go to the military, or is it going to be a civilian project? Is it going to be Department of Energy? A combination of things. Is it international or not? There's a lot of questions out there. So I'm going to summarize here. I like this slide very much. It's one of my favorite slides. And the first thing is, we can talk about, really making solar and wind bigger. That's nice, but you can see how small they are. And I'll mention again in a few slides resources intensiveness and how that slows how much you can utilize on those. Again, they're not bad. We want to certainly push them forward. Nuclear, you see, is a pretty substantial amount of electricity, but the problem with the nuclear is the industry is about capped out. You've got a, mid-aged industry. There's got things that have to be maintained on it. You got to have a lot of expertise. It's going to be hard to double the number of qualified nuclear engineers, PhDs, and increase the oversight to ensure that everything is maintained. So you might, expect out of that 100 or so nuclear power plants, another 4, 5, 10 coming online in the next couple of years, but it's not going to be substantial, and you don't want to mess with what's working. Okay, so you don't want to overstress that system, and of course you want to phase out what everybody considers mainly coal. See how much of it's electrical power. Natural gas seems to be being advertised quite a bit now. There's some advantages of it, but like coal, it's going to have a limitation of it. Plus, you have coal is used for, natural gas is used for other things directly, and there's only so much you can divert to your electrical needs. So even if you took the entire other band somehow from residential to commercial, which you wouldn't want to do, you have that problem. So there's a lot of losses in the electrical process there. That's an area that one would want to exploit. The limitation of conservation, again, is good, but look how small the line is of the unused energy. You're not going to change that much. I mean, there's some there, but the point is that that's not the critical factor. And of course, cars, transportation, large amount of fuel oil. You want to have a line from your electrical to that area, the cars and the freight. And someday maybe that line will be built. We're working towards that, I think, as a nation in the world, electric vehicles. But you're going to need power to power those electric vehicles. So that's your critical point, and that thickness of the line is about what you need, to maintain. You really need that kind of huge increase, and that's the problem the world faces. Of course, systems engineering. I haven't done a talk on systems engineering. I haven't thrown this slide. This is where we are: preliminary design, the conceptual stage. We've got to pick the right pieces now, because once they're set in motion, once you get into the hardware in your building, you want to go, we didn't pick the right piece. So there's a lot of decision-making trades, and of course, right now we have the least amount of data, the least amount of hardware, etc., available. So the decisions are hard. So what you got to look for is something that's the untouchable growth factor, something that when you get into the real-world engineering and you really throw some losses in there, and you really throw some safety factors in engineering and other stakeholders throwing requirements on you, no matter what project this is, military, civilian, whatever. Technology problem, you're going to have to be able to say, I'm going to maintain these 2 or 3 key growth factors. The biggest thing I point to lifter and for thorium is the fact that you can look at small scale. Smaller you go, the better for cost, okay, for flexibility, for overall usefulness. And we've seen that in computer power and other things. And the fact that manufacturing costs, handling, if you do in multiple cycles, you get a database so that a problem on one unit, like an aircraft, will alert you to a failure, a catastrophic failure coming up in some other aircraft. And you can go back and check, you know, what do you call it? We've got a little crack, or we've got some maintenance issue that shows up. You can't do that if you only have very large single units. It becomes very, very vulnerable, a risk to those kinds of failures. There's a whole bunch of other reasons why getting it down to a modular and a smaller size. And the reason why present reactors won't scale is the physics. You know, the Navy has made it about as small as a reactor they can in a reasonable package. So unless you go to something like a lifter design where you can actually go and give yourself some, again, breathing room on your design space and really be able to make smaller units and still be fairly efficient. What is lifter? What's the definition? And is it agreed upon, or are there a couple of different definitions for lifter and what it means? To me, it's a technology base. It's not one design per se. It's an area trade space that needs to be defined. Eventually, we'll get a little more detail into a specific, lifter design. But I consider it a category that's open to discussion and debate. This one, I mainly kept it for the four corners to remind you what are you trying to really solve here, and safety, compact mobile units. I think that's the key fundamental point needs to be stressed. If you compete against the very large units, and they did this in the 60s, it doesn't really necessarily mean there are not other competing technologies. And of course, proliferation and waste reduction, I'll talk about that a little later. That seems to be the hot topic. I'm going to go ahead and step through these things. Everybody knows how this works. You mentioned the grid interfacing. That's actually pretty good. We always talk about the reactor, but the electrical side of the house is just as important to the overall system effectiveness, and that's what everybody needs to keep in mind. It's not just the one part you're working on or the interesting physics. And of course, making it a timely covering the energy gap that you need to make a difference. Again, technical definitions. I think this wording actually was what was attempted on Wikipedia at one point, and they pulled it out. What is it? Is it high temperatures? Where is that categorized? Those kinds of things. A little more specificity in this, so that when we're all talking about this or presenting different pieces in the future, that there's a common base. I think that's really important to remember. Again, from the Google talk, and I will not go through these. I will try to, let's see if I can get one to go here. Go to the Brayton cycle. I don't think I mentioned this one there. Just that in a systems engineering step through, these are decisions you're going to have to trade. These are decisions that have to eventually have data behind them to say, is it air water cooled, or can they be both? Can you make a system that is interchangeable, where you just pop on the interaction of a heat rejection system? That would be nice. Being a thermodynamicist, I have my doubts. I think things have to be fairly coupled and well-defined, and that makes it a little bit harder. There are probably changes in the rest of the system that would couple from whatever your heat sink is and what that temperature is. High efficiency recuperator, that's a big one for, again, overall efficiency of the system, and how big or how much you put into that will determine the other parts of the system and what inlet pressure you're going to have. So there's a trade there. Again, on this slide, you're looking always, why do you care on heat rejection, independent location? All right, it sounds nice, but really what it means is flexibility where it's used, and it drives the cost, because you can use the same unit in different locations, independent of whether there's water there or not. The same unit on a naval vessel as opposed to civilian emergency, power system that's, brought out to a site after a disaster. Those kinds of things drive the cost if you can. So, again, in a systems engineering approach, you match those, and then you direct your actual data to prove, yes, that's true. There is a cost savings because of this. But again, what I've written here is inherent properties. The fact that you can independently move around means it should be lower cost, okay, unless you screw it up.